Hello and welcome Nord Anglia, and thank you for joining us today for our MIT abstract on solar panels, desert dust, and jump rope with MIT graduate student Stewart Isaacs. I'm your host, Fatima Hussein, and I'm a PhD candidate at MIT studying ancient Earth. Before we begin, I'd like to let you all know what an abstract actually is, and it's just a snapshot or a summary of a greater work of research or writing. And now I'd like to welcome our amazing speaker for today, Stewart. Stewart is a PhD candidate in MIT Aeroastro, and I am a huge fan of all of his work. Welcome, Stewart.
Thank you, Fatima. Great, let's get into it. So hello, everyone. My name is Stewart Isaacs. I'm a PhD candidate in aeronautics and astronautics here at MIT. And I'm going to tell you a little bit about how I got to do the research I'm doing currently and about myself and my journey to this point. And so I wanted to start in high school because I believe that a lot of you are going to be entering high school very soon, if you're not there already. And I absolutely loved high school. I had a ton of fun. I do competitive jump rope. So there's a picture of me on the left where I compete in things like freestyle and speed. And I show the best tricks I can do or how fast I can go with the rope. And with that, I get to compete and travel a lot. And so I was doing that a lot in high school. But in addition to jump rope, I was doing a lot of other things. So there's a picture of me playing drum set. I was in a rock band and a steel drum band. And I also played American football. And in addition to that, I was also actually doing schoolwork in high school. And so one of the things that we needed to do was a senior project where we would do 1 year long study on a topic that we chose. And because I wanted to do something that I thought was meaningful, but also something that I thought was interesting, I chose to do mine on the technology that could improve the environmental sustainability of airplanes. And so this is a picture of me on the right, giving that presentation at the end of the project. And I really enjoyed what I did. I looked at things like this airplane here, which use advanced technology to reduce the amount of fuel that airplanes use or reduce the emissions that it has. And I thought that this is great. It has a good impact on society. It's something that I've always been interested in, which is airplanes. And I think I'd like to continue doing this for college. So when I went to college, I attended Stanford University, and I actually ended up studying mechanical engineering. So this is a picture of Stanford on the left. It is a very beautiful campus. I really enjoyed being there, very warm too in California. And I did mechanical engineering because one of the faculty members actually recommended I do that instead. When I attended Stanford, they did not have an aerospace engineering undergraduate program fully built out. And mechanical engineering is very close because it's a very broad program. So there's a picture of a robot doing a backflip on the right. A lot of mechanical engineers will work on things like robots, but also things like airplanes and rockets as well, because it's a very broad topic that I can talk about more if you have questions later. And so in addition to doing studies, I also continued to explore my interests. Just like in high school, there was a lot of things I was curious about and wanted to learn more about. And so I did. I continued to do jump rope. So there's a GIF of me doing a jump rope with my team. I started Stanford jump rope because I thought this is a great sport that I think more people should be involved in it. And so we had a lot of fun doing that too. I also studied abroad in Santiago, Chile. So there's me with some friends at a football match, and we had a good time and I learned a lot, including a little bit of Spanish. And also I wanted to learn more about my identity, especially as a Black American. It was great to have an opportunity to learn more about African-American history at Stanford. And so I had experiences to not only take a class, but also lead a class in that. And so there's a picture of me talking to a civil rights leader for a class I led in the Deep South to learn more about the civil rights movement in the United States. But of course, I did engineering. I did several engineering projects. And like I said before, mechanical engineering was a good choice for me because I got to do things like rockets. And so there's a picture on the left of our final capstone rocket project that we had to do in order to graduate. And I had a really good time doing that with my team. And as well as this other project on the right, which I'm going to talk a little bit more about later, that really had a big influence on my life. And that was to build this solar powered chicken egg incubator. And so you see me on the right with my team. We worked together to kind of build a prototype to make this work. And let me talk a little bit more about what that meant. So for our work, we wanted to build this solar powered chicken egg incubator. And what an incubator does is it takes chicken eggs, so you can imagine the eggs that come out from the mother chicken, and it incubates it so it keeps the temperature warm and it keeps the conditions right so that it can hatch into these baby chicks like you see on the left. Turns out incubators are a little better at making sure the chickens go from the egg to the baby chick than the mother hen is, just because the mother hens are not always the most consistent at incubating the eggs. And so we want to build this and make it solar powered in this country called Burkina Faso, which is highlighted right here. It's on the continent of Africa. It's in West Africa. It's kind of near the Sahara Desert. It's also right above some other countries you might know, like Ghana or Cote d'Ivoire. And so our community partner, Barima, as well as this other person, Dr. Dina Montague, had this nonprofit together where they wanted to use solar energy to improve the lives of people in this region. And that's because in many parts of Africa, there's actually not a lot of access to electricity. So in Burkina Faso and other places, many people live without access to modern electricity. And even when they do have access, sometimes the lights cut out because the infrastructure just is not good enough to continuously support everyone using electricity. And so that was important for us because they wanted to use incubator technology to make sure that communities can continue to produce their own food, especially in a place where they're importing a lot of the chicken. And they needed to be solar powered because they didn't have access to consistent, reliable electricity. And a lot of people had no access to electricity at all. And so I thought, wow, this is a really cool project. This is exactly what I want to do. It's something I feel like I can be passionate about. And so I worked with my team to build a prototype, or essentially the first version of a product. And so we worked very hard. We put together the solar powered system. We were able to ship it to Burkina Faso from California. So it was very long travel. And we sent a team. I didn't go the first time, but we did send a team on the right to go put it together and see if it works. And unfortunately, it did not work. And so this was the end of my experience at Stanford. This was my senior year. And so it was really disappointing, but the story does not end there. So after I finished my undergraduate studies at Stanford, I went to graduate school at MIT. And here I was able to study aeronautics and astronautics. So you see a picture on the right of a rocket landing itself. That might be something that people would do in the aeronautics and astronautics department, where we look at things like rockets and airplanes and satellites, and a lot of other systems that are related to them, but maybe not directly them. And so this is a picture of MIT on the left. This is the iconic dome. It overlooks the river. It's in Boston, Massachusetts, in the United States. It's a very cool place to be in, lots of other college towns. And then here's a picture of me doing a backflip with the rope in front of the dome. I continue to do jump rope, although there's not a team with me at MIT, I still do it and have a lot of fun. And so when I started at MIT, I did a lot of different research projects. So one of them was designing an airplane that could fly off rooftops, and using different technologies like this shown on the right, where we can increase the amount of air that goes over the wings so that it flies a little better. But I also looked at things that were very similar to what I did in high school, which is what are ways that we can use technology to improve the environmental sustainability of airplanes. And so on the picture on the left is this picture of a device that is supposed to suck carbon dioxide out of the atmosphere. And then we're going to put it through several processes to eventually turn it into jet fuel. And so I looked at ways that we can do that, how much is it going to cost, and what the environmental benefit is going to be. And I made very fancy plots like this on the right so that we can see, well, if we were to do this process in different parts of the United States, how much exactly would it cost, and what would the benefit or disbenefit be from using these different technologies to do that? And I thought it was very cool, but I was still stuck on this problem of the solar power incubator because I worked with Barima and I really cared about making sure that, he got something that could work. And so I ended up traveling to Burkina Faso to go and try and fix the incubator. And so you can see the picture on the right of our prototype after we worked on it a little bit. And because it was very important to me that they get a device that's going to work so they can meet their needs, because I really want to make sure that people have access to technology they need to be able to eat and support their communities. And in the process, we learned a lot about how solar energy works in the community. Not only are they trying to use it for incubators, but they want to use it for things like lights, or to pump water, or to make sure that a hospital has enough energy so they can keep their vaccines and medicines cold. And so I saw how important it was, but I also saw some problems too. So one of the things that ended up happening is our incubator did not work again. So even after going back, it still wasn't working. And I was able to see that there's this other issue of dust that collects in the panels. So because Burkina Faso is near the Sahara Desert, sometimes a lot of dust comes into the region and it might collect in the panels or sit in the air. And so I began to think that this might also be impacting the ability of our solar incubator, as well as other things like lights, solar lights and solar pumps to work. And so I wanted to learn a little bit more about that. And so because I was frustrated at making these devices that weren't working, and I saw how important solar energy was, I wanted to make sure that I really understood what was going on locally. So I moved to Africa. I spent a year working at Ashesi University in Accra, Ghana. And there I worked with a team to kind of continue to develop solar power incubator prototypes and really understand what the environment was locally so that I can be a better engineer and serve the communities that I think need this technology. And so I had a good time there. I also wanted to continue to stay in Ghana to learn more. And so I spent a year teaching. So there's a picture of me on the right teaching some students as a teaching fellow at Ashesi University, and really teaching mechanics and thermodynamics and physics, but also learning from my students to learn about where they come from, what are the problems they're facing, and what role I might be able to play in terms of playing a role in helping them. One of the things I learned while I was there in Ghana was that the dust doesn't only collect in the panels, it's suspended in the atmosphere. And so they have this annual season called the harmattan. It's their dry season. And during the dry season, the dust comes in and it stays in the air. This is actually a picture taken in Lagos, Nigeria during their harmattan season. You can see it's very cloudy. And you can imagine that when you're trying to generate power from the sun, not as much sun is going to get through because of all the things in the atmosphere. And that can be a big problem. And so it's like, okay, now that I understand this, let's see if we can go back and address it. And so that's what I do now for my research. I look at the impact that dust is having on solar energy, and I consider it in two major ways. One of the ways is these dust were known as aerosols, and that's just a word that we use to describe particulates that are suspended in the air. And so we look at how much of the incoming sunlight is going to get reduced by the dust aerosols before it even gets to the panels, because that might be very significant, and that might be doing things like making it harder for our solar incubator to work. But I also look at this thing called dust soiling. So that's what happens when the particulates collect on the panels. So if you remember the picture you saw before where there was a bunch of panels that were covered in dust, that's that dust soiling effect. And that also is going to reduce the amount of power that the solar panels can produce. And so what I do is I use data from satellite images. So I work with researchers at NASA. NASA is one of the space agencies of the United States, and JPL is one of the locations that NASA operates out of. And a lot of them are really good at working with satellites. And so I work with those research engineers, and I use the satellite data to understand how much dust is in the atmosphere. And then I use computational models to crunch that data and understand, well, if there's this much dust, here's how much we think is going to collect on the panel, and here's how much that we think is going to be suspended in the air, and here's how much power we're going to be losing because of it. And with that, we can more effectively design things like solar incubators to really function while in this area. So here's an example of what this looks like. And we can see that actually dust is going to have a pretty big effect on the solar panels. What you're looking at right here is what we call the soiling ratio. And that's how much less energy we're producing because of the dust that collects on the surface of the panels. And basically, the darker blue it is, the less energy we're producing because of the dust. And so we can see using the satellite images and our computational models that some parts of the year, it actually gets really bad. We're making less than 50% or half as much power as we think we would get without the dust. And so that was just significant. We were able to learn a lot by just using the pictures and understanding how the dust is going to impact our systems. And because of that, we're actually able to produce a product that's going to work. So I continue to work with REMA and people in the community over several years so that we can design a system that's going to function. And we changed the design in some key ways, but one of the things I was able to do was say, okay, now that we can account for the dust and these other things, here's what size the panels need to be so that we get enough energy to produce the energy that you need to hatch the chickens. And so here's a picture of the locally produced incubators. We now have some in Burkina Faso that are locally produced and they work and they hatch chickens like you can see on the left. And here's a picture of what the system looks like all together with the batteries and the panel, as well as the eggs that eventually go in to hatch into chicks. And so this is something I'm very proud of. But again, this is not something that I imagined I would be working on. And so you can see that throughout my life, I can continue to choose things that I'm really passionate about and that I care about. And eventually that leads me to a place that I also really like. And so this is something that I feel good about. And that's something I want to continue to do. So in addition to working with Barima, I want to work with other communities so that we can use solar panels to really support them in getting what they need. So for example, here's a picture of a project I worked on. This is based in Kenya. And there they're using solar energy to keep vegetables cold, because right now, if you don't keep them cold, they spoil and you're wasting food. And this is a part of the world where people could really use the food that is being wasted. So we use solar panels to keep it cold, but also we want people to be able to use solar panels themselves to be able to support whatever goals they might have. And so I work with people who are also teaching people, maybe people around your age, to be able to build their own solar panels and to be able to do things like address dust or whatever problem that they might have locally in an effective way. So here's a workshop that was run in northern Ghana with some people that I know. And here's some solar panels that they actually made during the workshops. So we can see that hopefully this is going to continue to get better. But now I'm very happy to accept any questions that you might have. Thank you for listening to my talk.
Thank you, Stuart. This was super cool. And I really appreciated how you told us the story about continuing to work on those incubators until they worked. And it's really amazing to hear that there are working incubators in Burkina Faso now as a result of all the hard work you and your team and collaborators there put into it. So that is so inspiring and really wonderful. I'd like to kick off our Q&A with a question that came in almost immediately. We have a student who's wondering, how fast can you jump rope?
Good question. How fast can I jump rope? I think the best I've ever done is 210 jumps in 30 seconds, which is a little more than 3 jumps per second.
That is many times faster than what I can do. So that is really impressive. Could you tell us how you initially got into jump roping, and tell us a little more about what it's like doing jump rope at the level that you're at? Because, you know, when I'm jumping rope, it is up and down, up and down, up and down. But I think I saw you doing flips and your team was like doing backflips and jump. Is there music going on? Could you tell us a little more about this?
Yeah, of course. I started jump rope when I was 5 years old. My elementary school had a jump rope team. And so me and my sister actually wanted to join the team because it looked cool. And so we joined, and it just happened to be a competitive team. And so we learned a lot of skills. We learned how to do speed. So speed, again, is when you just go as fast as you can and as much time as they give you. So it might be 30 seconds, it might be 3 minutes. And then freestyle is the flips and things that you saw earlier. So that's just one of the coolest things you can do with the rope. And what I really like about it is it's an opportunity to be really creative, because almost anything you can imagine you can do with your body, you can do with the rope as well. And so the opportunities are limitless. And so people will flip, people will dance. There's usually music too, it's choreographed. It's a very good time, and it's something that I continue to do today. So actually, we were talking earlier, but I'm currently in France for a jump rope trip where there's an international double dutch competition, and I got to be with some friends here and had a really good time.
That is way, 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 way too cool. So I mean, it's amazing to hear that in addition to traveling to pursue the things you're passionate about in terms of research and applying your engineering background, you're also able to travel and pursue your passion of jump roping. And it's brought you to another continent, which is super duper cool. That leads me into the question that came in immediately after. And we have a student who asks, how do you find the time to do everything?
Oh my gosh. Yeah. Wow. Good question. How do I find the time? It can be challenging. I think for me, doing things like jump rope are kind of important. And so I'm always going to prioritize it because it's a sport I do that keeps me healthy, not just physically, right? So obviously jump rope is a lot of cardio and like it requires a lot of strength. So I need to keep my muscles strong in order to do it well. But it's also really good mentally. You know, it really helps me think clearly. I won't be able to be as effective in my research or my studies without it. So I just prioritize it to make sure I do it. In terms of the other things, I don't know. I don't watch a lot of TV. I suppose that might free up some time. But it's a good question. I'm still trying to answer the question because sometimes I do more than I can actually, I take on more than I can actually do. So very good question, because I'm still trying to answer that.
That is totally fair. I think everyone's always figuring it out.
Definitely.
Yeah, but I think it is really cool that you're in a place that you're able to pursue all of these things, even though sometimes you can overextend, which will happen to all of us, even, you know, before we get to college and in school in general. So it is cool to see how other people approach it. And now I wanted to shift us over to the science a little bit. You told us about the installation of these solar panels and the issues that came with it, like that desert dust. So we have a few questions from students about this. So let's get into that. We have a student who's wondering, does this dust problem affect solar panels in other parts of the world?
Yes, absolutely. Great question. So a lot of places with a lot of dust will also look into this. So one of the biggest places producing research right now is from the Middle East. So places around the Arabian Peninsula are also very interested in the problem of dust on solar panels. And so there's a lot of really good literature coming from there. But even in the United States, in places like Arizona, even up to Colorado, because of the deserts around that area, people are interested in looking at, okay, what is the impact of this dust and how can we solve it? So any place where there's deserts, which is interesting because those tend to be the sunniest places on the planet too, right? So those are the places that you want to put the panels, but they're also impacted by this other issue of dust. And most times people will clean it, but sometimes there's other technology too that you can use to clean it off.
And so you can put solar panels in a lot of different locations for a lot of different purposes. And a student is wondering, can we use solar panels to stop food waste in other places? Or what are some other applications of solar panels that you've been able to work on or think about?
Yeah, I think this is another good question. Typically in places like the US or in Europe, when people talk about solar panels, they talk about these giant installations. So we're looking at like gigawatts of panels, hundreds of rows of panels. And what those will do is they'll be plugged into a grid, right? Because there's like an existing infrastructure and it's gonna support making sure that households have energy. Or people might put it on the roofs. And so that might support one household, but it reduces the amount of energy that they're pulling from the grid. In places where there's not a lot of existing grid infrastructure, so they might not have the telephone poles with wires to hook up the houses, people might use it directly to support different services. And it's a little different. And I think I just want to make sure that we make sure that a little different the way that panels can be used. And so, yes, we can do things like incubators. One thing that's very popular is pumping water. So what people will do is they'll take a pump and they'll put it down into basically a ground source of water, and they hook it up to a solar panel so that they can continuously pump water out to support their agriculture. They might be growing tomatoes, or they might be growing something that needs a lot of water in a particularly dry place. And so I've seen it actually have a pretty big impact on communities where they might not have reliable sources of water. And then you can use the solar powered water pumps to make a reliable source, and now you can grow more food, which is good, but also causes other issues that we don't need to get into yet. In addition to that, you can keep things cool. I'm trying to think of maybe one of my favorites. I think really growing plants with solar powered water pumps is one of the most exciting things that I've seen lately.
Oh, that sounds really cool and potentially like really, really impactful, because it is such a hard thing to pump water that takes a lot of energy for sure. So I think that could be really powerful. And of course, people in these sunny places, they'll have those solar panels for their farms near their water sources, but they're also going to deal with that dust problem, right? So there's a lot of things you have to think about. And one of the things that I'm wondering is, when you're going to these communities or thinking of these applications and, actually traveling to Africa and working with folks there, do the local folks have involvement in the design process? Do you start working with them well before you actually reach there? How do you identify collaborators? And then could you tell us about the relationships you might have with farmers and the folks who actually, like, for example, hatch the chickens and need the chickens?
Very good question. I think that was one of the biggest things I learned from working in Burkina Faso, is that a lot of people on the ground there kind of understand the solutions. Like, this is what we need to make it work. They might not have the resources or the opportunities to pursue those. And so that was important in getting the incubator to work, because, we spend a lot of time just like, okay, how do we get the humidity and the temperature to be right? But people already knew how to do that. That wasn't the problem. The most valuable thing I could offer is like, let's get the sizing of the panels correctly. And so it's very important to keep local people involved in the process, because a lot of times they're going to be the people that offer the best solutions many times. And then certainly another part that I didn't talk about as much is they're going to be the ones to maintain the project as well. So the reason that I had that picture of the solar panels covered in the dust is because actually what happened is a foreign group brought in a bunch of solar panels to power. It was actually behind a hospital to keep medicines cold, and something broke and no one locally could fix it. And so it literally collected dust because it was broken. And so it's very important to keep local people involved in the process, because they need to be able to understand how the technology works so that when something goes wrong, they can fix it. Or even better, maybe they can improve it to be working better than you might have even imagined. So for us, when we went and traveled, we met with a lot of people who were also involved in like incubator technology. And like that's really how the solution came together, is because we kind of all pooled our resources and knowledge together to get to something that eventually was going to work. With some of the other projects, I haven't always been the lead on the project. But again, the story is always consistently like in the Kenya project, for example, we were working with a company that, had engineers, and they were also linked up with people who were really good at solar. And then we're also linked up with people in India who were also doing something similar. And so, just pulling all of our resources together to be able to make something that is going to work and be sustainable is always a key for this to work well. I don't know if that answers your question.
No, I think that does. And one thing that I'm a little struck by in the process of, putting yourself in those environments, working with folks, having those conversations about how do we keep this technology going, what knowledge are you bringing into it, and how can we work together? I think that's such a cool demonstration of international teamwork and collaboration. And that sounds like it really sets you up for success, so that folks in these communities can continue to use this technology, fix it by themselves, for example. And that as a result, people are still going to be able to use those incubators, and they still do to this day. So I think that's a really wonderful result. One of the things I'm curious about, and this is taking that solar panel technology and thinking about it in a very different environment. So bear with me for a second. You've described for us really well this issue of dust accumulating in these solar panels, and it sounds they reminded us in the team about there's a similar dust problem on Mars, and I think there's some folks in AeroAstro who think about that. Could you tell us a little bit about it? I think some of the Nord Anglia students have been introduced to this problem during one of their Nord Anglia challenges called MOXIE. So they learned about the MOXIE instrument with Jeff Hoffman, who's in your department.
Yeah.
I'm wondering if you could kind of tell us about if you studied this situation at all off Earth, or what you know about that.
Yeah, great question. It's definitely an issue on Mars and the moon as well. And that's actually some of the very first research projects looking at how do we solve this problem of dust were from the aerospace community on things like the dust on Mars or the dust on moon things. Because when we send rovers, so actually the people I work with, NASA JPL, they also produce these really complicated robots that will land on Mars and then operate. And sometimes the limiting factor is when the solar panels get covered in dust, they can no longer get energy, they can no longer continue to work. So people definitely have considered, what is the impact of this dust collecting on the solar panels on Mars, right? For our rovers that are very important and very expensive. And how do we solve them? So I think the MOXIE project is absolutely something that uses similar like analysis to understand the impact of the dust. And it's also another very important use case for understanding the impact of Martian dust in this case. I also like the MOXIE project because it also connects to some of the other research I've done too, right? Where now you're converting carbon on the Martian surface into fuel that you could use to power rockets to send you back to Earth potentially. And so it has some technology that we can also use on Earth to reduce the environmental impacts of airplanes on Earth as well. So there's a lot of connections between the problems that come up in space with the problems that can really support life on Earth as well. And I think that's one of the most beautiful parts about being in this department is that usually, something that may not seem relevant is really relevant. And maybe just one other story is that's actually how solar panels came to exist. Solar panels were initially designed to function, to be an energy source for systems in space. And then we realized that we can use them on Earth as well. And now it's transforming the world.
I did not know that. That is way too cool. And I think, when you first learn about solar panels, you get really excited because everywhere that you get sunlight, you're like, could I put a solar panel here? And I'm wondering, I'm going to ask you some wild questions here.
Let's do it.
Could you put a solar panel on a rocket, or is that a really bad idea?
Oh, interesting question. I think the way that people would do it is kind of how they do it with satellites now, where you have your package inside the rocket, and then once you get into space, you kind of unfold the panels to get the energy. So that's typically how you might have seen some of these really large telescopes that have gone up to space recently, like James Webb, and they'll kind of have the origami to spread out, and then you get like the solar panels to power all the online electronics for the telescope. That's probably the way to do it. The key there is you need a material that's going to be light and something that's not going to take up that much space, because sending things to space is very expensive. And you need to make sure the materials that are on the outside of the rocket are also going to be able to withstand the very high temperatures and pressures that you're going to experience during the launch. So the way to do it would to put it inside and then unveil it once you're in space. So you can definitely do it.
Okay, that's cool. And we have a student who's wondering, so you told us about, the project you worked on with that rocket engine and seeing that. They're wondering if you're ever going to get back into that side of things as well, or if you're like on solar panels now, like, will you ever make a rocket again is the question that one of the Nord Anglia students needs to know.
Will I ever make a rocket again? I don't know, maybe. I think one of the things that excites me is that, a lot of the biggest aerospace development work happening is really concentrated in places like the United States and Europe. And we haven't really seen the full. I would love to see more people involved in aerospace within the continent of Africa. And if building rockets is a part of that, I'm all for it, right? I would definitely be building rockets with people, as students to support their understanding of how aerospace might be able to support their needs, on the ground there. So it's possible. Plus, it's just a lot of fun. It's interesting. So I could see myself doing it. I will also say, one other thing I did that I didn't talk about is this other form of rocket. It's called electric propulsion, where basically you take electricity and you use it to accelerate special gases in order to produce thrust. And so I did a couple summers working on that. And that's one way you can use solar panels on rockets to get the power you need to be able to go very fast. That also might be something that I could work on too. It's something I have worked on, and I wouldn't mind doing it again.
That is super cool. We have a question that just came in from a Nord Anglia student who's wondering, what was the hardest issue you faced in your engineering projects? Could you tell us about like a really difficult challenge you came across and how you got through it?
Good question. Let me think about that for a little bit. The hardest issue I faced. Maybe I can talk a little bit about that rocket project. It was very hard. The whole class was actually really tough. We spent a lot of time. Friday nights, we get together, we do the computational models, and really the rocket project was the culmination of all that work. And so there was a lot of issues that we faced, and it required a lot of creativity too. So one of the things, like in order to be able to win the competition, so it was a competition and it was to see which team could produce the most efficient rocket. And we got opportunities to test it to see how efficient our rocket was. And so we figured out early on, the more we test, the better, more likely we are to get in a very efficient rocket, right? And so one of the things that we decided to do was like, if we can come up with faster ways to be able to build the rocket fuel, then we can test more and we can increase our odds to win the competition, right? So we were coming up with ways that, okay, if we print out these shapes that are going to allow us to manufacture a little faster, maybe we can get into the lab more to win. Another thing is that you actually need all the parts to fit spec. So they need to be very precisely the right shape in order to fit into all the equipment in order to do the test. And a lot of times teams will show up and their parts are out of spec, including us, right? We can only do so well to like manufacture, but sometimes it's like, oh, it's out of spec, you can't test. So one of the things that we did was like, well, we know that materials change, they expand and they constrict depending on the temperature, right? So sometimes we be out of spec and we're like, put it in the water bath. So we do like the hot water bath to like make it expand just a little bit. It's like, okay, now we're in spec. Now we can test, right? And so again, those are some challenges that we had to really get creative and think about how can we solve this. Even the design of the shapes, we're like, how do we get this shape? And so we just tried a lot of different things until something worked. And I think a lot of the engineering process is like that. Like people think I think people underestimate how creative the process can be. You can just kind of have any idea, test it. It might work, it might not, but that's okay. You learn no matter what.
And one thing you mentioned in the process of telling the story is something I want to ask about. So you told us that you would get together with your team on Friday night and start working on the computer with them. Can you tell us what a day in the life of like Stewart is like? What's a typical day for you?
Wow, yeah. Undergrad was a little different. Undergrad was a lot different actually. These days, my days are waking up 7:30. Usually what I do is I stretch in the morning. I'm pretty involved in sports, and so I need to make sure my body is healthy, and especially if I'm going to be sitting a lot. I make my breakfast. I'll read some recent research papers. So I have Google Scholar alerts that will send me papers that are relevant to the work I do. And so I go through, I see like, okay, are there any ones I think are good today? It's like, oh, yes, there are. And so I might read them for a little bit. And then I start my day. I make a plan for all the things I need to do today. I check my calendar. I say, I have these many meetings. I have these deadlines coming up. I told myself I was going to work on research for these many hours on Tuesday. So today's Tuesday. I'm going to allot these hours. And then I try and like plan all my day. So usually I'm working at home or in the lab for a few hours, some time for research, maybe a meeting or two. And then by the end of the day, at 5 o'clock, I go to gymnastics. So I'm currently on the club gymnastics team. I decided to try something new. I'm doing jump rope, but I also do gymnastics. And so I'm there for 2.5 hours. I eat dinner. And then I might have some meetings afterward, actually. So sometimes I run a student group that we meet in the evenings and there's dinner with it. Or I'm also an RA on campus. So actually I live with undergraduates and sometimes we meet to make sure that things are going okay. Or I might have a event for the undergraduates, like giving them snacks and stuff.
Oh, that's very nice. And it sounds like a busy day, but I think you're showing us that if you plan it out and be intentional about what you want to do, then you can manage to do a lot. And also still have fun, because I imagine gymnastics practice can have some pretty fun moments. It sounds like a lot of flips might be happening,
Yes.
which seems totally cool. One thing I wanted to ask you about something you mentioned in your presentation. You mentioned that, during your graduate studies at MIT, you took a year and moved to Accra, Ghana. And a lot of students on this call, might go someplace really different for college, or they might, switch schools, or at some point in their lives find themselves in a new place. And I'm wondering if you could tell us a little bit about, how you managed to orient yourself, on a new continent, in a new environment. How did you make friends? Could you give us some advice for those who might, have those changes coming up in our lives?
Yeah, absolutely. And I will say that it's pretty similar in a lot of stages of my life, right? Moving to MIT, I didn't really know anybody. Moving to Stanford, I didn't know anybody. I spent a quarter in Chile. Actually, I did know some people. But I think for a lot of it, it's being open to new opportunities or new experiences. I think that was offered a nice way to meet people, both at MIT and when I was in Ghana. I think really putting myself out there to be able to have experiences where I interact with others was a good way to meet folks. I think staying connected with people back home was really important for me too. So I would actually schedule some time to talk to family or talk to really close friends. I think that played an important role, especially when things got hard, because things are not always easy, and they're not always that fun. They can be kind of hard sometimes. And I think also I think really those are the two main things. It's like, what can I, staying grounded with the people from back home to make sure that I'm okay. And then really putting myself out there to have new experiences. Sometimes, especially at MIT, I did notice like maybe there's a gap that I think there needs to be something here, and I just don't see it yet, right? At Stanford, now it's Stanford jump rope, right? Where it's like, we could do so much. We have the potential. We don't have it. Let's do it, right? Let's put together Stanford jump rope. Let's make a group. At MIT, similarly, it's like, I think, there could be a space for this. Let's make that space together. And so I started, got involved in some groups where we can bring people together and really have community. Because for me, community is actually really important. And so a similar thing in Ghana, I didn't really have an opportunity to like put new groups together, but I did have an opportunity to, really get to know some people, have some new experiences, and make some really some lifelong friends too.
It sounds like just being open to new experiences is such a crucial part of moving and orienting yourself. But it also seems like that makes a lot of sense in research, try new things. Think about, missing components here. What can you do? What can you fill in? What jumps can you make? I think that sounds really, really important and really interlinked with all these different parts of your life. Now, I wish I could keep asking you tons of questions, but I know that you have this double Dutch competition you got to get to. So I'm going to leave you with one more question. And I think there's a lot of students on this call who have heard about all these wonderful things you've managed to do as an engineer, and they think, hey, maybe I want to be an engineer one day. And I wonder if you could leave them with some insights about what good qualities do engineers have that they can cultivate.
Yeah, I think you probably saw in the story that being persistent is important. Being persistent with the incubator technology in order to get it to work was, that was required, right? And so doing things that also require persistence, things like jump rope is actually also really hard. Can help, develop that skill to make you a good engineer. Being creative can be helpful too. As I talked about with the rocket project, we had to really come up with some creative solutions to some challenges so that we can get to the result we wanted. And so doing things that like also support creativity can be nice to develop that skill set. And I think ultimately, honestly, I'm not the most career-driven person, which might seem bizarre because I'm getting my PhD in aerospace engineering, but I just continuously make choices that make sense to me in the moment in terms of what I'm really passionate about. What can I really throw my energy into and think I'll get a lot of fulfillment out of it. And I think that can also be a good way to lead oneself into the engineering field, right? If it's like, yes, I really love this kind of technology. I think this is something that I could really get a lot of fulfillment from. It makes a lot of sense, but it doesn't need to be, I need to be this certain way just because people told me to. Like, I think following your interests and passions is important too.
I think that is really, really good advice. And I want to thank you for sharing all of that with us today and for sharing your experiences with us. Now, you talked about so many different things today that I think a few of us are going to need to watch the recording as well to really fully capture some of the amazing, amazing things that you've done. So I want to tell the Nord Anglia students on the call that if you want to rewatch any part of Stewart's talk today and his amazing presentation, or catch any of the other past MIT abstracts, you can find those on Global Campus or on YouTube. So be sure to check it out there. And now I'd like to thank our sponsors for our series, the Nord Anglia Education MIT collaboration, for making this series possible and for giving us the opportunity to bring amazing folks like Stewart to this series. Thank you so much to everyone who has joined us. Thank you to the students for asking really wonderful questions. And lastly, thank you so much, Stewart, for tuning in all the way from France, while you're at this jump rope competition to share your story with us and for inspiring us. I really appreciate it.
Thank you so much for having me. I really appreciate being here.
Yeah, well, best of luck, and I will see everyone in our next abstract. Bye, everyone.